For 4.6 billion years, we thought we understood how our solar system was born. Comets were supposed to be frozen time capsules from the primordial chaos, simple mixtures of ice and rock that told a clean story of cosmic evolution. But in 2015, the Rosetta spacecraft shattered that comfortable narrative when it detected something that should not exist. Comet 67P was bleeding molecular oxygen into space. Not trace amounts, not contamination. Pure molecular oxygen that had somehow survived since the dawn of time. Here is the problem. Oxygen is the ultimate chemical rebel. It bonds with everything it touches, especially hydrogen, which was everywhere in the early solar system. Finding free oxygen on a 4 billion year old comet is like finding an ice cube in a furnace. The discovery does not just challenge our models of planetary formation, it suggests our entire understanding of chemistry in space is fundamentally wrong. And if we are wrong about something this basic, what else are we missing about the forces that created our world? Stay until the end to discover why this impossible oxygen might be the key to rewriting the origin story of everything we know. The European Space Agency's Rosetta mission was humanity's most ambitious comet chase. For over a decade, the spacecraft travelled 4 billion miles through the void to rendezvous with Comet 67P Churyumov Gerasimenko. This was not just another flyby mission. Rosetta was designed to orbit the comet for months, sending a lander to its surface and studying its composition in unprecedented detail. Scientists expected to find a dirty snowball, a primitive relic that would confirm our textbook understanding of solar system formation. The mission was supposed to be routine archaeology, digging into the frozen archives of cosmic history. Dr. Catherine Altweg and her team at the University of Bern were tasked with analysing the comet's chemical composition using the Rosetta mass spectrometer. This state-of-the-art instrument was designed to identify the molecules escaping from the comet's surface as it warmed under the sun's heat. They expected to detect water vapour, carbon dioxide, and simple organic compounds. Standard comet stuff, nothing that would challenge 4 centuries of astronomical theory. But as Rosetta approached its target in August 2014, the instruments began picking up readings that made no sense. The mass spectrometer was detecting molecular signatures that should not exist on a primordial object. The team initially dismissed these anomalies as instrument errors or contamination. Little did they know they were about to stumble upon a discovery that would shake the foundations of planetary science. The first anomaly appeared in the preliminary data sweeps. The Rosetta instrument detected molecular oxygen at concentrations of from 1 to 10% relative to water. In cosmic terms, this was massive. Comets are not supposed to carry free oxygen. They are supposed to be chemically reduced environments, dominated by hydrogen and simple compounds. The presence of molecular oxygen was so unexpected that it did not fit into any existing model of comet composition. But here is the catch. Oxygen is the most reactive element in the known universe. It does not just sit around waiting to be discovered. It bonds instantly with hydrogen, carbon, and virtually everything else it encounters. In the hydrogen-rich environment of the early solar system, free oxygen should have been consumed within millennia, and if not sooner. Finding preserved molecular oxygen in an object 4.6 billion years old defied every principle of chemical thermodynamics. The team ran the analysis again, convinced their instruments were malfunctioning. The readings came back identical. Comet 67P was hemorrhaging molecular oxygen into space. The implication was clear and almost too radical to accept. This oxygen had somehow survived in its molecular form since the solar system's birth. It gets worse. The oxygen was not just present, it was primordial. Isotopic analysis showed that this molecular oxygen had been locked in the comet's ice since the solar system formed 4.6 billion years ago. The oxygen molecules showed no signs of recent formation or chemical alteration. They were original components of the comet, preserved like insects in amber, from a time before Earth existed. Dr. Altweg's team faced an impossible puzzle. They knew oxygen could not survive in the early solar system's chemical environment. The nebula hypothesis, our standard model of planetary formation, describes a hydrogen-dominated disk where reactive elements like oxygen would be instantly consumed. Free oxygen should be as rare as diamonds in a sandbox, but the data was irrefutable. The oxygen concentrations were consistent across multiple measurement sites on the comet. This was not contamination from Earth or from the spacecraft. This was not a localized anomaly. This was indigenous oxygen that had somehow defied the laws of chemistry for billions of years. Here is the deal. The discovery violated everything we thought we knew about cosmic chemistry. If oxygen could survive primordial conditions, then our models of how planets formed, how atmospheres developed, and how the building blocks of life were distributed throughout the solar system were fundamentally flawed. This was not a minor correction to existing theories, it was a wholesale invalidation of basic assumptions. The team published their findings in Nature in October 2015. The scientific community erupted in controversy. Some researchers accused the team of misinterpreting their data. Others suggested the oxygen was produced by recent chemical reactions, not primordial preservation. The pushback was intense because the implications were too profound to easily accept. But the evidence kept mounting. The oxygen was there, it was ancient, and it was impossible. The more the team analysed their data, the more certain they became that they had stumbled upon something that challenged the very foundation of planetary science. The Rosetta mass spectrometer is not a toy. This instrument can detect individual molecules and determine their precise composition and origin. When it identified molecular oxygen on Comet 67P, it was not making a guess. It was providing a chemical fingerprint. The spectrometer measured not just the presence of oxygen, but its isotopic ratios, its concentration relative to other compounds, and its distribution throughout the comet's emissions. To put that in perspective, detecting molecular oxygen on a 4 billion-year-old comet is like finding a newspaper from ancient Rome that is still readable. The chemical environment should have destroyed it eons ago. Molecular oxygen in space is typically found only in regions of active star formation, where energetic processes temporarily generate it before it is consumed by chemical reactions. Finding preserved molecular oxygen in a primordial object is like discovering a burning candle inside an ancient Egyptian tomb. The European Space Agency confirmed the findings through multiple independent analyses. The oxygen was not just present in trace amounts, it represented up to 10% of the water content in some regions of the comet. This was a major chemical component, not a minor anomaly. The concentrations were orders of magnitude higher than could be explained by any known process of oxygen generation in cometary ice. They ruled out contamination because the isotopic ratios did not match Earth's atmosphere or the spacecraft's systems. Earth's oxygen has a distinct fingerprint due to biological activity, and the comet's oxygen showed none of those markers. They ruled out recent formation because the oxygen was distributed throughout the comet's interior, not just on the surface where solar radiation might create it. This oxygen had been there since the beginning. The team analysed the correlation between oxygen and water vapour emissions. What they found was shocking. The oxygen and water were released together in fixed ratios, suggesting they had been frozen together since the comet's formation. When the comet warmed under the sun's heat, the water ice sublimated directly into vapour, carrying the trapped oxygen molecules with it. The correlation was so precise that it implied the oxygen had been incorporated into the comet's ice matrix during the solar system's earliest stages. This was not oxygen that had somehow survived on the surface. This was oxygen that had been protected in the deep interior for 4.6 billion years. The relationship between water and oxygen emissions was so consistent that it could only be explained if they had been frozen together from the start. Dr. Andrei Bieler, a co-author of the study, confirmed that the oxygen showed no signs of chemical alteration or decay. It was as pristine as if it had been manufactured yesterday, despite being older than Earth itself. The oxygen molecules were not degraded or partially reacted. They were intact, complete oxygen molecules that had somehow evaded chemical combination for eons. The measurements were so consistent that they ruled out any known process for oxygen production in comets. Solar radiation, cosmic ray bombardment, and chemical reactions with other compounds could not account for the concentrations they observed. The oxygen was not being generated by ongoing processes, it was being released from primordial storage. The first suspect was contamination. Scientists initially assumed the oxygen readings were artifacts from Earth's atmosphere or the spacecraft's propulsion system. It was the safe, comfortable explanation that preserved our understanding of cosmic chemistry. Contamination is a common problem in space missions, and it is always the first explanation considered when unexpected compounds are detected. But the data showed clear contradictions. The isotopic signature of the oxygen did not match Earth's atmosphere. The concentrations were too high and too consistent to be contamination. The release pattern correlated perfectly with the comet's water cycle, not with spacecraft operations or orbital positions. The oxygen was indigenous to the comet. With contamination ruled out, scientists had to consider more radical possibilities. Some proposed that the oxygen was produced by radiolysis, the breakdown of water molecules by cosmic radiation. This process can generate oxygen in space when energetic particles split water into hydrogen and oxygen. But calculations showed that radiolysis could not produce the observed concentrations over the comet's lifetime. The oxygen production rate would be orders of magnitude too low. The most mind-bending theory is the primordial preservation hypothesis. This suggests that molecular oxygen was actually abundant in the early solar system, but our models of nebular chemistry are completely wrong. Instead of a reducing environment dominated by hydrogen, the solar nebula might have contained significant amounts of free oxygen that was somehow preserved in the cold outer regions where comets formed. Dr. Altweg and her team proposed that the early solar nebula was far more chemically complex than previously thought. Instead of a simple hydrogen-dominated environment, the nebula might have contained pockets of oxidizing conditions where molecular oxygen could form and persist. These oxygen-rich regions might have been protected from hydrogen by unknown physical or chemical barriers. But here is the catch. This theory requires rewriting the fundamental principles of stellar formation. It suggests that the collapse of the solar nebula created chemical environments we do not understand, governed by processes we have not discovered. If true, this would invalidate decades of research on protoplanetary disks and force a complete reconsideration of how solar systems evolve. Some researchers have proposed even more radical explanations. The oxygen might be evidence of exotic chemistry involving quantum effects or non-equilibrium thermodynamics. These processes could allow reactive molecules to survive in conditions that classical chemistry says should destroy them. Perhaps at the ultra-cold temperatures of the outer solar nebula, oxygen molecules become trapped in quantum states that prevent normal chemical reactions. The implications are staggering. If oxygen can persist in environments where our models predict instant annihilation, then the early solar system operated under completely different rules than we assumed. The chemical processes that formed planets and ultimately enabled life might have been nothing like what we have been teaching in universities for generations. The Rosetta oxygen discovery proved that our understanding of cosmic chemistry is fundamentally incomplete. This is not just about one anomalous reading. It is about the possibility that the universe has been hiding its true nature from us for centuries. What we thought were iron laws of chemistry might be mere guidelines that break down under extreme conditions or over cosmic timescales. This means the chemical processes that formed planets, created atmospheres, and enabled the emergence of life operated under principles we do not recognize. The building blocks of life might have been distributed throughout the solar system by mechanisms we have not even imagined. The very chemistry that made Earth habitable might be based on processes we have failed to account for in our models. But the question that haunts cosmochemists is deeper. If we are wrong about something as basic as oxygen survival in space, what other impossible chemistry is happening right under our noses? Are there entire classes of chemical reactions occurring in the cosmos that we are blind to because they violate our Earth-based understanding of how molecules behave? This discovery does not just challenge our understanding of comets, it forces us to reconsider everything we think we know about chemical evolution in space. The standard models of planet formation, atmospheric development, and the origins of life might all need fundamental revision. We have been building theories on assumptions that the Rosetta mission has now proven false. So, do you think the Rosetta discovery proves our models of solar system formation are catastrophically wrong? Or is there an undiscovered chemical process that allows reactive molecules to survive in impossible conditions? What if this oxygen anomaly is just the first crack in a cosmic conspiracy that has been hiding the true nature of chemistry in space? What if the universe operates on principles so alien to our experience that we have been studying a shadow of reality for centuries? The oxygen on Comet 67P might be evidence that the cosmos is far stranger and more chemically active than we ever dared to imagine. And if that is true, then everything we think we know about how worlds form and life emerges needs to be reconsidered. Let me know your theory in the comments. If you want to keep exploring the impossible discoveries that are rewriting science, smash that like button and subscribe for more cosmic mysteries that challenge everything we thought we knew about reality.